the difference between the Higgs mass and the Planck mass is literally the root of action.
You finally flipped.
This is alpha, the fine structure constant. Its approximate value is this. Some argument once you get to the last digit, but that's we'll pass over that for the sake right now. So that definition is the whole thing that we have on the board there. E squared 4 pi c epsilon naught h bar yada yada yada. Okay, so let's try to simplify this. So let's just do elementary charge divided by the Planck charge. Square the thing. Oh, look. This appears to be the same number. Huh. 0.00729735256. 0.00729735256. Oh, that seems to be computationally equivalent. Imagine my shock. Yes, that's a charge pun. All right. So, having that as a bit of knowledge, I decided, I'm like, well, what happens if I did something similar? So, why is the Higgs mass much smaller than the Planck mass? Let us attempt to do science. We just asked the original question, so we have Higgs mass or the Planck mass. You get that 10 to the 17 number. I have no idea what that is. So, but, I don't know what that is, but if I'm going to take some intuition from the fine structure constant, what do we have? We've got an elementary thing divided by a Planck thing, squared. So, I decided to do just that. Just throw our little protective brackets around it, we square it, and then we get this number here. Okay. Now, most folks, this number, 1.05 times 10 to the minus 34. That shouldn't mean a dang thing to anybody. All right. Because also, if there's one thing I've learned from Sean Carroll, it's all good physicists set h bar equal to 1. And in one of his videos, he even says, like, if you ask me the value of what h bar is, I don't know. Because all good physicists set h bar to 1.
By the way, you might want to know, what is the number, Planck's constant? It's some number of joules, seconds, whatever it is. I have no idea what it is because every good physicist sets h bar equal to 1.
Since I'm not a good physicist, and I don't usually set h bar to 1, unless in the particular case, I recognize at least the first 3 digits and this magnitude. This happens to be the first 3 digits and corresponding magnitude to, let's go over here, h bar, make a new window. So we just literally type in h bar, the elementary unit of action, which, let's, more digits. So as we can at least see here, the first 3 digits are 1.05 times 10 to the minus 34. Now, again, it has dimensions there, but that's a very interesting thing. It's like, wait a second, it's got the first 3 significant digits and the correct corresponding magnitude to the elementary unit of action. Huh. Okay. For those that have stuck with us, we're getting to the punchline. Okay. So I looked at that, I'm like, what if I assume this was true? If we assume there's some there, then what we can do is, all right, well, let's set this equal to, so since this is a mass, and we're dividing a mass, this is going to give us a dimensionless relationship. So we're going to take h bar, the elementary unit of action, and we're going to divide it by its reference of action, which is the joule second. Where do I get that from? Well, it literally says it here. It's expressed in units of energy seconds. So that may seem arbitrary, but is it really arbitrary? Because, well, if this number isn't arbitrary, and it's literally in reference to this, well, if this is arbitrary, then this is arbitrary. And we use this all the time. We literally consider this a 1 within our system of measure. Huh. And this is just a reference one. See, that was part of the argument that we need to make a little bit better. So what I'm doing is I'm taking this number, I'm dividing it by this number, and let's actually see what happens when we get that. Okay, it's giving us the dimensionless number. And let's do this. All right, so we've got these things here. We're going to assume it is equivalent to the magnitude of action. So all we do is, the Planck mass is defined. We get about 5 or so significant digits of confidence in there. We got 7, but there's error bars. So let's literally just solve for x, just like that did. X, and this is in kilograms because it's a mass. So I just solve for x. Go through here, it does the mathematics and stuff. You get this number here, okay. So this number here, and note, it's interesting because it does actually give us a positive and negative solution. So perhaps that's significant, perhaps it isn't. I'm going to include the different versions in the paper. But, so this is kilograms. So we're just going to attach the kilograms that we solve for. So we get this magnitude in kilograms, which is, oh, lucky. That seems to be about the mass of the Higgs boson. Well, that's interesting. But again, that's only 3 significant digits. All right. So if we did our little energy conversion, we do the c squared. We're going to get, all right, about 125.37-ish GeV. All right. But wait, there's more. So if we use the Eugene notation, we're going to take h bar, the elementary 1 of action. We're going to divide it by the Joule second, the reference of action, and then we're going to take the square root of it, aka we're going to be taking the root of action. You see what I did there? All right. So we're literally taking the root of action, and it gets us about 10 to the minus 17. Wait a second. Wasn't that the relationship difference between the Planck mass and the Higgs mass? Well, let's just see. Let's just multiply it by the Planck mass. Oh, lucky. So again, that's of the magnitude of the Higgs mass, 125.38 GeV. Now, why might that be an interesting number? Okay, let's go into why that might be an interesting number, because if we go to CERN's CMS collaboration, shout out to them because they actually won the Breakthrough Prize recently. So if we take the most recent CMS, the compact muon solenoid physics analysis summary for the combined measurements of the Higgs boson. Okay, so right now, the best fit has the mass of the Higgs boson to be about 125.38 giga-electron volts. What do we have over here? Oh, 125.38 giga-electron volts. That's interesting. Now again, the actual number that we get is, when we put in all the most recent stuff from CoData, it's actually not, it rounded up to 125.38 giga-electron volts. But right now, we do this notation of literally, I'm just taking the elementary unit of action, h bar, we're dividing it by the reference of action, the Joule second. We're taking the root of action there, and then we multiply it by m sub p. We're going to get, so the whole question, why is the Higgs mass so much smaller than the Planck mass? It's 17 orders of magnitude difference. Who ordered that? Well, maybe the root of action did? Because right now, if it's getting that, and our most recent measurement is from CMS, that's equal to 125.38 GeV divided by c squared because it's a mass. All right. That means that our difference, and again, I'm not great at math or anything, but even I can do this. We match for 1, 2, 3, 4 significant digits. And then the fifth, well, to be fair, this ends up being a difference of 4 MeV mega electron volts divided by c squared. So it's literally off by a mega electron volt is 1,000th of a giga electron volt, because at least when I remember from being educated at state school is once you get to the decimal point, we have the tens, the hundredths, and the thousandths. So we literally need to go into the thousandths of giga electron volts to see the difference. So it's within about 2 sigma of that estimate there. And again, here's the thing. There have been measurements at or around this, but at least for me, and again, could be completely wrong, and again, this might not be anything at all. It might just be a very interesting coincidence. But when you look at the measurements, it's like, all right, 126 GeV, 125-ish, and so the measurements seem to be kind of clustering around this area. And as Vanessa from the monastery said, nature is simple. Might, rather than having to add all these different amplitudes together and then all these correction factors, this, that, and that, the difference between the Higgs mass and the Planck mass is literally the root of action. That can't be right. That would be too simple. We need lots more notation. We need lots of crazy things here. And again, some rando can't figure this out. I mean, that's heresy. Well, Heretics Inc. it is then.